Hello and welcome to this online talk for ICALP 2020. My name is Jakob Piribauer and I'm going to present joint work with Christel Baier. The title of this work is on Skolem-hardness and saturation points in Markov decision processes. Let me begin by talking about a Markov decision process, MDP for short first. So a Markov decision process combines probabilistic and non-deterministic behavior, and hence is very useful to model things like probabilistic programs, dynamic power management, fault-tolerant systems, and many more. And furthermore, it allows us to also model quantitative aspects such as costs, time, utility, or energy consumption, for example. Here I depicted an example, and for us, a Markov decision process consists of a finite set of states and a finite set of actions. And in each state, like the state U here, we have the choice between different actions, here between alpha and beta. And this is a non-deterministic choice. And once we choose an action, say beta, this transition probability function here tells us which successor state we will see with which probability. In that case, with probability 1/2 we will move to S, and with probability 1/2 we will move to goal. Furthermore, we have an initial state here, and whenever we choose an action in a state, we collect some weight, as each state action pair has an integer weight. So for example here, if we choose beta in U, we collect weight +1. To move through the system, we need a scheduler, which is a function that resolves the non-deterministic choices. So given the finite history, the scheduler tells us which action to choose among all the possible actions that we can choose in the current state. And once the scheduler is fixed, the system is purely probabilistic. Okay, in the formal verification of probabilistic systems, we often encounter optimization problems on Markov decision processes, and a very typical such problem is the stochastic shortest path problem, which is the following. We're given an MDP-M with a weight function, and we ask what is the minimal or maximal expected accumulated weight before reaching a goal state. For example, if we want to know the worst or best case expected termination time of a probabilistic program, where worst or best case means worst or best possible resolution of the non-determinism, then we end up with such a stochastic shortest path problem, for example. In the classical setting, we only consider schedulers that reach the goal with probability 1, then the expected value is well defined, and the problem is solvable in polynomial time by linear programming techniques. However, if we, for example, look at an error scenario which occurs with some small probability, and we want to analyze the energy consumption of the repair mechanism which is triggered in case that error scenario occurs, then of course we don't want to consider schedulers that reach goal, so the activation of this repair mechanism with probability 1, but schedulers which reach this situation with small probabilities. And then we somehow have to treat the paths that don't reach goal. In the paper, we look at two such non-classical variants of stochastic shortest path problem. The first one being the partial stochastic shortest path problem, in which we simply assign weight 0 to all paths that don't reach the goal. The other problem is the conditional stochastic shortest path problem, where we look at the expected value under the condition that goal is reached. So in other words, the average expected accumulated weight among all paths that actually reach goal. And both of these problems have been studied in the literature, and for both of these problems it is known that they are solvable in exponential time if all weights are non-negative. While in these problems we look at the optimization of the expected value, of course often we are also interested in guarantees on the distribution of path lengths. For example, we want some bounds on how large the risk is to encounter very high accumulated weights. And an established risk measure to do exactly that is the conditional value at risk, which roughly speaking is the average weight of the p worst path for a given fraction p, like 5% for example. In the probabilistic setting, it usually doesn't make much sense to look at a worst case analysis, so the conditional value at risk is a good way to quantify how bad cases are. And the conditional value at risk has been studied on MDPs recently by Kretinsky and Meggendorfer for a weighted reachability problem, which essentially means that we only collect a terminal weight once we reach the goal state, but we don't accumulate weights before. And for such weighted reachability problem, the optimal conditional value at risk can be computed in polynomial time. Other type of optimization problem that typically arises in formal verification is the probabilistic model checking problem, which is the following. We are given a Markov decision process M and a specification phi, for example given by an automaton or in some logic, and the question is, what is the maximal or minimal satisfaction probability of the specification in the system? For linear temporal logic specifications, for example, this problem is 2x time complete, and typically the verification questions on finite state MDPs are decidable. To encounter undecidability results, we usually have to look at either recursive MDPs, for example, which are infinite state, or partially observable MDPs, or we somehow have to deal with multiple weight functions or multiple objectives. So, in recent years, there has been an increasing interest in quantifying the degree to which a specification is satisfied, not only in terms of the satisfaction probability, but also other approaches. And a logic which came up is the logic frequency LTL, which extends linear temporal logic with a frequency operator, this globally greater theta of phi. And this globally greater theta phi holds on a path if a fraction of more than theta of the suffixes satisfy phi. So if the fraction of time at which the specification holds is greater than theta, roughly speaking. And this can be very useful to argue about the long-run behavior of the system in equilibrium. After some initialization phase, if the system runs forever, typically reaches some kind of equilibrium, and then these frequency operators can be used to distinguish which behaviors occur often in the long run and which don't. And a notion which goes into similar directions is the notion of long-run probability, where instead of looking at the fraction of positions or the fraction of time at which the suffix is, where we look at the average probability that the suffix satisfies the specification. So also this notion is useful for reasoning about the long-run behavior and the system in equilibrium. Okay, I promised some Skolem-hardness results in the title, so let me tell you what the Skolem problem is. The Skolem problem is the following. We're given a natural number k and k many rationals alpha I and k many rationals beta j, and we define a linear recurrent sequence from these rationals. We simply let the initial values be the values given by the betas, and all further members of the sequence are then computed as a linear combination of the previous k members. So un plus k is a linear combination of the previous k members of the sequence, and the alpha i's are just the coefficients of this linear combination. The most prominent example, of course, are the Fibonacci numbers, where you have some initial values 1 and 1, for example, and then each further member of the sequence is the sum of the previous two. The Skolem problem now simply asks, is there a natural number n such that un equals 0? This problem is also closely related to the positivity problem. In fact, the Skolem problem is reducible to the positivity problem, which asks whether the sequence stays non-negative for all natural numbers n. And although these questions look rather simple, they are not. Both of these problems have been open for many decades, so the decidability of these problems has been open, and it is known that any algorithm solving the Skolem problem, and that's also any algorithm solving the positivity problem, would imply a major breakthrough in number theory. And this shows that apparently these problems have a very high inherent mathematical difficulty. We say that a problem is Skolem-hard if the Skolem problem is reducible to that problem, which witnesses that this problem has also this high inherent mathematical difficulty. So this brings me to our surprising results, which are that the series of the optimization problems I presented has Skolem-hard threshold problems. And the threshold problem simply asks whether the optimal value is bigger than a given threshold. And this applies to all these variants of the stochastic shortest path problem, the partial and conditional stochastic shortest path problem, as well as the conditional value at risk. And it also applies to long-run probabilities already for quite simple regular causation properties, and the model checking of frequency LTL also for simple fixed frequency LTL formula with only one frequency operator, and then a simple fixed LTL formula afterwards. So in the remaining time, I want to sketch how this Skolem-hardness proof works, and I also want to talk about saturation points, which allow us to compute the optimal values in restricted versions of all of these problems. So to sketch the Skolem-hardness proof, I will use the partial stochastic shortest path problem. As I mentioned, we simply assign weight 0 to all paths that don't reach goal, so we look at the random variable which assigns the weight to a path if the path reaches goal and 0 otherwise. Then the partial expectation of a scheduler is simply the expected value of this random variable under the scheduler, and the maximal partial expectation is then the supremum over all schedulers. The threshold problem now simply asks whether the optimal value is bigger than a given rational theta. Okay, so we know that there are optimal weight-based deterministic schedulers for this partial expectation, which means that the scheduler only has to take the current state and the current accumulated weight into account to make a decision which action to choose, but nothing more is important from the history. So only the accumulated weight is important information. So it makes sense to write the partial expectation of the scheduler as when starting in state t with accumulated weight w. Because whenever we are in state t with this accumulated weight, the scheduler will behave in exactly the same way. So now, let's have a look at this part of an MDP. In fact, as it is shown here, it's only a Markov chain, but later we will add other outgoing actions to these states t and s. But now any scheduler has to choose this action gamma here. And then we want to compute the partial expectation when starting in state t with weight w, for example. So we know that with probability 1 minus alpha 1 minus alpha 2, we reach goal immediately here, in which case we collect weight w. With probability alpha 1, we move to state t1, from which we will return to state t with weight minus 1. So we can plug in the partial expectation when starting in t with weight w minus 1 here. And with probability alpha 2, we can move over to the state S2, where we lose weight 2 and move to state S. So we plug in the partial expectation, starting with state S with weight w minus 2 here. Okay, so that's rather simple, but why is it useful? It's useful because if we look at the difference between the partial expectation when starting in state T and starting in state S with weight W, then we can simply compute that this difference is alpha 1 times the difference 1 weight level below minus alpha 2 times the difference 2 weight levels below. And we achieve that we have a minus here simply by switching states here. And this is a linear recurrence relation. So this is the key gadget to encode linear recurrence, which we will use. So let me just very quickly show you how to continue. So we add some other outgoing edges to these states T and S here. For different weights, we have different actions, and all the probabilities are fine-tuned such that the following scheduler is optimal. The scheduler chooses the action gamma j if the weight is minus k plus j plus 1. For j at most k minus 1, so for some negative weights and weight 0, one of these actions, gamma j, is optimal. But for all positive actions, this action gamma here is optimal. If we choose such an action gamma j, then everything is worked out such that we reach goal with a small probability, and that this probability is beta j higher if we start in T than if we start in S. And that goal will be reached exactly with weight plus 1 if we choose gamma j and end up in goal. So in that way we can also encode the initial values of a linear recurrence sequence and obtain that the difference between the partial expectation here and here is exactly the linear recurrence sequence given by these beta j's and these alphas here. Of course, if we want to encode more than a linear recurrence sequence with depth more than 2, we can just simply add more states here in the same fashion. Furthermore, we take the scheduler, which is optimal up here, and let it always choose action tau in the state C down here. And the state C is reached from the initial state with arbitrarily high weights with positive probability. And the idea now simply is that the maximal partial expectation is at most the partial expectation of the scheduler, which we can compute, and which is irrational, if and only if the scheduler is optimal. But this scheduler is optimal if always choosing tau here is optimal, and that is the case if and only if it's always better to start in state D than to start in state S, which is the case if this difference is always non-negative. And this is exactly the positivity problem, the question whether the linear recurrence sequence is non-negative, and in that way we can reduce the problem whether the given linear recurrence sequence is non-negative to the threshold problem for the partial expectation. And we can reuse this gadget encoding the linear recurrence relation also to show similar results for conditional threshold problem and the conditional valued risk, and surprisingly also for these long-run notions, the long-run probability and the model checking problem of frequency LTL. And this means that we cannot compute the optimal value in any of these for any of these problems unless we come up with a major breakthrough in number theory. But nevertheless, there's at least also some positive result here, and this is that there are saturation points. Of course, that was already known for several of these problems. But let me sketch what a saturation point is for the conditional value at risk. So, as I mentioned, the conditional value at risk is an established risk measure, also known as expected shortfall or tail loss, and it answers the questions what to expect in bad cases. So let's denote by weight of pi the weight before reaching goal state, and we consider high weight to be bad now. And the value at risk is then defined as follows. So we're given a fraction p, scheduler and an MDP, and the value at risk is then the value such that exactly p of the path have an accumulated weight which is the value at risk or higher, and 1 minus p of the path have a weight which is less than the value at risk. So there's a quantile, it's the least number such that the probability to have a higher weight is still at most p. And the conditional value at risk is then the expected weight of a path under the condition that the weight is bigger than the value at risk. In other words, it is the expected weight under the condition that the path belongs to the p worst outcomes. And this is all a bit simplified, but essentially that's the idea. So now let's have a look at an MDP-M with non-negative weights such that the minimal probability to reach goal is 1, and we're given such a p. Now the question we want to answer is, what is the maximal conditional value at risk? And the reason why we're interested in the maximal conditional value at risk is because it is some kind of upper bound for the risk. And we do that in the following way. We compute a number WP, which has the property that starting from any state, the probability to reach an accumulated weight higher than WP is at most P. And this is quite easy, because under this condition we can estimate how long paths can become before reaching goal, or the probability that paths are long is getting small very quickly. So we can compute this WP in polynomial time, but WP itself will be of exponential size typically. And then we can look at the following representation of the MBP here with the different weight levels here. So here are all the states of the MBP, and here is the weight which is already accumulated. And if we reach this weight level WP, then we know that we already belong to the P worst paths, because at most P of the paths ever reach this weight level. And this is why we call this a saturation point, because now it is clear what happens if we want to maximize, what has to happen if we want to maximize the conditional value at risk. We simply have to maximize the expected accumulated weight before reaching goal as soon as we are up here. And this can be done by a memoryless deterministic scheduler. If you're down here, then of course we cannot simply maximize the expected weight, because we want to maximize the tail loss, and so of course we can sacrifice some of the expectation to do that. But as soon as we are up here, then the best thing we can do is to maximize the expected value by a memoryless deterministic scheduler. And so we can simply plug in the value of this scheduler here. So we know that if we reach this state here, we have already weight WP collected, and in expectation we will collect the maximal accumulated weight which is possible, expected accumulated weight which is possible from the state on. And if we are in goal, then of course we can simply plug in the current weight level. In that way we reduce the problem to a weighted reachability problem. This is a weighted reachability problem of exponential size, because this WP is of exponential size, but we know that this is now solvable by the techniques provided by Kretinsky and Meggendorfer, and this gives us an exponential time algorithm for this problem. And the key feature of the saturation point is that once the saturation point is reached, there's a memoryless scheduler which maximizes our objective. Okay, and this allows us to solve all of these optimization problems in restricted versions. For the stochastic shortest path problems here, this is simply by only allowing non-negative weights, which was of course already known for partial and conditional stochastic shortest path problem. And for long-run probabilities, if we only look at this very simple co-safety property A until B, this is doable. And similarly, for some frequency LTL formulas of this form, we have the frequency operator and then an until, we get decidability, and this formula was not in the fragments for which the model checking problem was already known to be decidable. So let me quickly summarize what we have seen. We have seen a novel reduction from the positivity problem to threshold problems in MDPs, and all of these reductions use this one gadget to encode a linear recurrence relation. And surprisingly, this reduction can be applied to a series of optimization problems which don't seem too related on first sight. And furthermore, many of these problems had been studied in the literature, and we could now at least give some answer to to the questions which remained open there. And of course, it would be very interesting to see whether we can find more optimization problems on MDPs where this reduction is applicable. And maybe we could also characterize the properties of these optimization problems which make this reduction work to get a more general understanding. Furthermore, we have seen that for restricted versions of these problems, especially for the conditional value address, we can use the saturation point to solve the problem if weights are non-negative, or if we look at rather simple properties for the log notions. Thank you very much for your attention. Here, a quick view of the references, and I'll be very happy to answer questions during the time slot I'll be assigned to in the conference week. Thank you.